Hi, my name is Haley Harrington, and we are the Texas Instruments Water Reclamation Team.
I'm Brooke Hazard.
My name is Kira Lawrence.
My name is Scott Repecki.
My name is Susan Yato.
First, we'll be going over the project background. The facility we're working at is the Texas Instruments Dallas facility outside of Dallas, Richardson, Texas. The process that we're looking to improve is the chemical mechanical planarization process, otherwise known as CMP. This process uses deionized water and a mixed slurry composed of silicon dioxide and water to polish semiconductor wafers. This process can be seen next to me. It also produces a mixed effluent waste stream. The process is expensive and wasteful, wasting both slurry and water. The main objective of our project is to recycle as much of the water in that mixed effluent waste stream as possible.
The market and competitive analysis for Texas Instruments shows goals for in-house manufacturing, for aiming about 95% of manufacturing to be done in-house and spending $4.82 billion in 2024 to help achieve these lower long-term costs. This creates an advantage against fabless competitors like Qualcomm and Broadcom, and creates larger goals than those of competitors with fabrication facilities like Analog Devices. This project was split up between 2 semesters, so for the first semester the team focused more on a broad scale of understanding of the process and our model, since there were a lot of changes in scope during this time. For the second semester, the team was able to dive into the technical aspects of this project with verifying the efficacy of the model and testing the samples and updating our model programming to fit these tests. On the report side of this semester, the team was able to dive into the details and get a better understanding of the scope, which helped us update previous chapters and sections to fit the scope changes from the first semester.
For process synthesis, we systematically developed and refined a treatment pathway for the CMP wastewater, starting from a broad set of potential technologies. We evaluated several separation methods, including distillation, membrane distillation, dialysis, and depth filtration, and these were screened using important engineering criteria like energy consumption, scalability, and compatibility with CMP wastewater. Many of these options were eliminated pretty early on due to high energy demand or lack of scalability for semiconductor manufacturing. An important design decision involved evaluating centrifugation versus vacuum filtration for solid removal. So we conducted experimental analysis using absorbance measurements to quantify particle removal efficiency. And the results showed that vacuum filtration did not provide any measurable improvement beyond centrifugation, and this was likely due to the filter pore size being insufficient to capture the remaining fine particles. Similarly, depth filtration was evaluated but eliminated due to its limited effectiveness for fine particle removal and lack of additional benefits after centrifugation. Based on these results, we removed these additional filtration steps, simplifying the process and eliminating unnecessary equipment. The final decision consists of a 2-stage system: centrifugation for solid removal, followed by reverse osmosis and ion exchange to remove the dissolved species and achieve deionized water quality that is suitable for reuse.
Looking at the budget, Texas Instruments gave the team $1,500 at the very beginning of the year, mostly for laboratory spending and other testing. About half of our budget has been spent, with around $662 left, and all of this has been used towards laboratory feasibility testing to test the process the team's designed.
Just as we described in the project background, the CMP waste effluent stream will be the influent stream for this process. Directly after the influent stream and between each of the processes, there will be 3 intermediate tanks. They were included to account for the plant running 24/7, 365, so we can have constant operation and places to store the water during shutdown and maintenance. This process includes 3 sub-purification processes. The first is a centrifuge, meant to remove anything above 1 micron in diameter. The second is the reverse osmosis filter, which is meant to remove anything between 0.2 and 1 microns in diameter. And the third is the ion exchanger, which is meant to remove any ions that could cause the water to be out of spec for deionized water standards. Finally, for this process, we have 2 effluent streams. The first is going to be our product stream, stream number 14. which is consistent of our deionized water put back into the CMP process, that has a resistivity of greater than 18 megaohms centimeters at 25 degrees Celsius, and it has a conductivity of less than 0.05 microsieverts per centimeter with less than 10 parts per billion of silicon dioxide. Our second stream is going to be our waste stream number 15, which is sent to TI's waste management facility that they already treat their own waste at.
So to optimize our process, we conducted a design of experiments, or DOE, to determine which operating parameters most impact the performance. We used a 2-level factorial design with 4 factors and 8 simulation trials, and analyzed the results using standard least squares and jump. Our 2 response variables were water recovery and ion removal efficiency. The factors that we tested included pretreatment performance, inlet solid concentration, and operating conditions for reverse osmosis and ion exchange. Water recovery showed strong statistical significance, while ion removal efficiency was not statistically significant, as the performance remained consistently high across all the conditions. For water recovery, the model showed strong statistical significance with an R-squared of 0.97, and the key drivers were pretreatment solids removal efficiency and the solids concentration entering the system. So this indicates that improving solids removal reduces the fouling and improves the downstream performance, particularly in reverse osmosis. So overall, this reinforces that pretreatment is an important step in maximizing system efficiency. For future work, expanding the DOE with additional runs and factor levels would improve statistical confidence and also allow for a more detailed analysis of the system behavior.
Now shifting into sustainability, one of Texas Instruments' sustainability-driven goals in 2024 was to conserve 2.8% of the past year's total water usage. Reports from TI also indicate that their water consumption has steadily increased since 2020, emphasizing the need for water reuse systems throughout their plants. Since our process aims to reclaim water that is typically labeled as waste, we are directly aligned with Texas Instruments' commitment to sustainable water consumption. To evaluate the overall sustainability of the process, we first looked at performance across 7 AICHE metrics. Social responsibility scored the highest due to community benefits like improved water security, while strategic commitment and product stewardship scored the lowest due to reliance on corporate-level decision-making. Key opportunities to improve include researching biodegradable resins and membranes, performing greenhouse gas calculations, and doing a full life cycle assessment on the processed water. Now, looking at the 3 pillars of sustainability, from a social perspective, the system reduces strain on the local water supply and improves water security, which benefits the surrounding community. At the same time, however, it does introduce additional risks for operators who must deal with additional chemicals and work with routine equipment like the centrifuge. Economically, the process does not generate direct revenue, but it does still provide value through reducing water purchasing and improving resource efficiency. Finally, from an environmental perspective, the process provides a clear benefit by reducing wastewater discharge, which is a major improvement. However, this comes with a trade-off, including additional waste streams from membranes and resins. Overall, our process represents a meaningful sustainability improvement at the Texas Instruments Dallas location, furthering their commitment to sustainable water consumption.
Getting into the safety assessment of the project, the entire process was split into 5 distinct categories, looking over the different unit operations and the piping associated with those. The hazards identified in each section are present here, but most of the major issues come with the reverse osmosis unit and the outflow piping leaving the process. This mostly falls into the category of process safety and a lot less personal safety, since the process is only dealing with solids buildup in the form of silicone and water leaving the process. To mitigate many of the risks present in the process, the team is looking to install a series of pressure and flow gauges throughout the entire process to make sure that water isn't flowing too quickly and to make sure that pressures stay where they're supposed to. In addition, routine maintenance and trained operators are going to be needed in this facility to make sure that all unit operations and instrumentation is working as it should be and that nothing is exhausting before it should be. Once again, most of the issues we see here are present in the reverse osmosis and outflow piping, so this is where a majority of the safety mitigation and checks will be conducted.
Per the safety recommendations, the team was able to design a PNID with 5 different control loops to account for those recommendations. The level control loops measure the levels within the intermediary tanks and adjust the flow rates to ensure that it does not exceed capacity. The pressure control loops measure pressure drop changes across the reverse osmosis membrane to see if there are any damages to the membrane or fouling. The conductivity control loops measure the exiting conductivity levels from the reverse osmosis and ion exchangers to ensure that the exiting water meets the desired specifications.
Finally, getting into the techno-economics of this process, the team looked at the overall cash flow that the project would bring into the Texas Instruments facility. We determined that a 10-year lifespan would be reasonable, but with this 10-year lifespan and how much instrumentation would cost, the payback period of the entire process would be over 197 years, not making the process economically viable for Texas Instruments. However, if the team were to scale up the process and clean water for the entire plant and not just the CMP outflow process, then the payback period would reduce significantly and it might become more economically viable for Texas Instruments. Therefore, if they choose to pursue water reclamation in the future, we would recommend that it is over a large plant scale rather than just the CMP process.
In conclusion, our team effectively designed a water recycling process for the Texas Instruments Dallas location. The feasibility of this process was validated through experiments and model optimization. We also improved sustainability performance and process safety through targeted design changes and automated controls. While the process does not generate direct revenue as designed, increasing capacity could yield meaningful cost savings for the Dallas facility. Future work includes incorporating advanced separation technologies such as electrodialysis, expanding optimization models with additional factor levels, and researching biodegradable resins and membranes. Additionally, performing a life cycle assessment on the processed water and identifying ways to improve cost savings will further strengthen the process. Ultimately, our project highlights the balance between sustainability, safety, and cost. Thank you so much for listening to the Texas Instruments Water Reclamation Team's Engineering Days video.